1 minute ago, a massive, horrifying torrent of volcanic mud began cascading down the slopes of Mayon volcano in the Philippines. Most terrifyingly, this is not the result of a traditional volcanic eruption. This disaster stems from something far more insidious, a geometeorological event unfolding right now. Twin super typhoons have coordinated their impact, simultaneously unleashing billions of gallons of water onto volcanic peaks. This immense rainfall has completely saturated ancient ash deposits, accumulated over decades, transforming them into unstoppable, highly destructive torrents of liquid concrete. The ground beneath the communities is not just shaking, it is actively flowing. And what is happening right now across the Philippine territory has never been recorded at this specific scale and nature in history. This is an unprecedented double disaster event. Two super typhoons concurrently triggering volcanic Lahar flows across multiple peaks. Within hours of the storms making landfall, the Philippine Institute of Volcanology and Seismology, PHIVOLCS, was forced to issue emergency Lahar advisories. But the issue extends far beyond a single volcano responding to a single storm. For the first time in recorded history, two Category 4+ typhoons struck the Philippines within a short 6-day window. These two storms dumped catastrophic rainfall, almost simultaneously, across various volcanic regions. The catastrophe began with Typhoon Calmegi, making landfall on November 3rd. This storm swept across the Visayas region, with sustained winds reaching 148 kilometers per hour. Notably, the storm's eye passed directly over eastern Samar, positioning its most intense rainfall bands precisely over dormant volcanic slopes. These were areas that had not seen significant ash mobilization in decades. Before recovery and damage assessment teams could even properly evaluate the initial losses, Super Typhoon Wong slammed into northern Luzon just 6 days later, on November 9th. This second storm packed sustained winds of 215 kilometers per hour, accompanied by a severe atmospheric pressure drop. However, meteorological data revealed something far more ominous. Wong's massive 1,800-kilometer storm diameter meant its destructive rainfall bands extended and simultaneously covered 3 major volcanic systems: Mayon, Canlaon, and multiple other volcanic peaks throughout the northern archipelago. The real threat in this situation was not the ferocious wind. The real threat lay in the water. Meteorological stations recorded rainfall totals exceeding 392 millimeters in Catanduanes alone. That is more than 15 inches of rain poured down in just 24 hours. Similar, extremely high precipitation rates struck volcanic slopes across 3 major island groups. All of this water fell directly onto ash-coated peaks, places that had not experienced this level of water saturation since their last major eruptions. PHIVOLCS, volcanologists, monitored their seismic stations. They observed signatures they had never seen before. These were not earthquake tremors. They were the continuous, powerful vibrations of massive debris flows activating simultaneously across multiple volcanic drainage systems. The volcanic ash, which had lain dormant and harmless for decades, suddenly became weaponized, rushing towards the communities below. But that is only part of the story, the part we can measure. It is the part that explains how stormwater transforms inactive volcanic material into deadly flowing concrete. Volcanic lahars are not lava. They are something potentially far more devastating, far more formidable. When torrential rain hits loose volcanic ash, pumice, and rock debris on steep mountain slopes, it creates a flowing mixture. This mixture has the consistency of wet concrete, yet it moves at the horrifying speed of a freight train. The physics of this phenomenon are terrifyingly simple, yet the scale at which it is currently operating is utterly unprecedented. Volcanic soil absorbs water in a fundamentally different way than regular earth or typical geological material. The ash particles, some of them microscopic remnants from ancient explosive eruptions, create an almost frictionless slurry when they become completely saturated. The composition is key. Much of this material consists of volcanic glass fragments. These fragments possess irregular, sharp surfaces that, when mixed and fully wetted, drastically reduce the internal friction between particles to nearly zero. This lack of internal resistance is what allows the flow to achieve such devastating speeds and momentum. Now, add the crucial factor of the steep gradient inherent to volcanic cones. Take Mayon, for example. It rises a staggering 2,463 meters almost directly from sea level, over a horizontal distance of just 15 kilometers. This geometry has essentially built a perfect delivery system for geological destruction. The average slope angle of approximately 30 degrees means that gravitational acceleration approaches maximum efficiency for initiating and accelerating debris flow velocity. Satellite imagery captured on November 9th revealed something truly extraordinary. It showed Lahar channels activating simultaneously across 3 separate major volcanic systems. The Mayon drainage basins, which are typically dry during the month of November, transformed within hours of peak rainfall into massive brown torrents clearly visible from space. Similar terrifying flows were triggered around Canlaon Volcano, a peak where recent volcanic unrest had already loosened its surface ash deposits, making them even more susceptible and vulnerable to water mobilization. Philippine atmospheric data further confirms the precise mechanism of this disaster. Wong's massive eye wall passed directly over Mayon's summit at the point of the storm's peak intensity. This meant the volcano's upper slopes received the most concentrated precipitation rainfall intensity, reached a staggering 50 millimeters per hour at the exact moment it was needed to trigger failure. The result was purely gravitational. Millions of tons of volcanic debris suddenly became mobile. This immense mass followed pre-carved channels toward populated valleys below at dangerous velocities, in some cases reaching 40 kilometers per hour. Unlike typical volcanic eruptions, which usually provide hours or even days of seismic warning signs like ground swelling or gas release, Lahar flows triggered solely by external rainfall can begin with almost no notice at all. The only true warning is the rain itself. And by the time residents hear the characteristic low, rumbling sound, a sound often mistaken for distant thunder or low-flying military aircraft, the flow is already moving rapidly downslope, carrying everything substantial in its path. The Lahar flow carries everything in its path: sturdy trees, entire vehicles, and even large multi-story buildings and terrain, features that seemed permanent and secure just minutes before. Yet, what comes next in the aftermath of these storms could be even worse, because history shows these flows do not simply stop when the rain ends. The terrifying and instructive example is the 1991 Pinatubo Lahar crisis, which continued claiming lives for years after the actual eruption had ceased. In 1991, Mount Pinatubo erupted explosively, ejecting an estimated 5 cubic kilometers of material and blanketing surrounding provinces with volcanic ash up to 200 centimeters deep. The initial eruption itself tragically killed fewer than 300 people, but the subsequent Lahar flows, which were repeatedly triggered by seasonal rains, killed thousands more over the next decade. Every single monsoon season, from 1991 all the way through 2001, heavy rains would remobilize Pinatubo's colossal ash deposits. The volcanic material had been deposited in a perfect storm of geological vulnerability: steep-sided valleys, vast quantities of loose, unconsolidated ash, and existing drainage patterns that efficiently funneled water directly through heavily populated areas. Entire towns, including Angela City, Arayat, Olongapo, and dozens of smaller rural communities, found themselves repeatedly buried under flowing volcanic mud. This deadly torrent arrived faithfully with each significant rainfall event. Critically, the Lahars did not follow predictable, existing paths. They violently carved new channels, jumped existing riverbanks, and buried vital infrastructure that engineers had considered safely distant from the original eruption zone. Communities that miraculously survived the initial cataclysmic blast found themselves under constant, debilitating threat from an insidious enemy, an enemy that struck without warning whenever storms approached. Survivor accounts from that dreadful decade consistently described the same warning signs. First came the sound, a low, persistent rumble that residents initially often mistook for distant thunder or perhaps military aircraft taking off from the nearby Clark Air Base. Then came the smell, a strong sulfuric and metallic odor, like wet concrete mixed with rotting vegetation and a chemically acrid scent that burned the nostrils. By the time families could visually confirm, the brown, imposing wall of debris approaching often 3 to 5 meters high and moving faster than any person could run evacuation was frequently no longer possible. The Lahars moved with such incredible density that they were able to carry entire houses, heavy vehicles, and 30-meter-tall trees as if they were nothing more than floating corks. When the flows finally stopped, they did not just leave soft mud. They left behind a concrete-hardened surface that required industrial excavation equipment to penetrate. Recovery teams found tragic evidence of the flow's speed and power. finding victims buried under Lahar deposits that had hardened to the consistency of sidewalk pavement. The core lesson etched into the memory of the Philippines from Pinatubo was starkly clear. The volcanic threat does not terminate the moment the eruption stops. Instead, every significant rainfall event becomes a potential trigger for renewed, deadly flows, remobilizing the same loose ash deposits year after year until natural erosion finally manages to stabilize the slopes. Some Lahar channels around Pinatubo remained active and dangerous for more than a decade after the initial eruption, tragically claiming additional lives with each major storm season that swept through the area. And now, scientists and emergency managers fear that history may not just be repeating itself, but it is doing so across multiple volcanoes simultaneously. We are now observing multiple volcanic systems being primed for ongoing Lahar activity right across the Philippine archipelago. The current situation represents something far more complex and dangerous than the single volcano scenario witnessed at Pinatubo. We are talking about three major volcanic systems, Mayon, Canlaon, and smaller peaks across Luzon and the Visayas, all having fresh ash deposits saturated and destabilized by an unprecedented volume of rainfall. The geological threat has multiplied exponentially. Emergency responders have already confirmed active Lahar flows in at least 4 major drainage basins surrounding Mayon volcano alone, with additional flows being reported near Canlaon and smaller volcanic peaks throughout the regions affected by the typhoons. These flows have immediately isolated several communities in Albay province, cutting off primary road access and tragically forcing emergency helicopter evacuations from areas that were considered geologically stable just 72 hours ago. Unlike the planned preemptive evacuations ahead of the typhoons, which successfully relocated 1.4 million people using established protocols, these current rescues are reactive. They are desperate attempts to save people from areas where no specific evacuation plans for a sudden Lahar event existed. Emergency teams on the ground describe Lahar-affected zones as moonscapes, where familiar terrain has been completely transformed by flowing volcanic debris that has since hardened into unrecognizable geological features. The cascading infrastructure damage already reveals the destructive efficiency of the Lahars. In addition to the 78 confirmed typhoon fatalities, emergency teams report hundreds of additional people missing in specific areas, where Lahar flows intersected with existing storm surge and floodwaters. Search and rescue operations have had to be suspended in some valleys, because the sheer volume of volcanic mud remains too unstable for ground teams to safely navigate. Furthermore, the hardened deposits are often too dense and rigid for standard rescue equipment to penetrate effectively. Official damage assessments currently show 105 roads and 46 bridges rendered impassable across the affected regions. But these numbers fail to capture the longer-term, devastating implications. Many of these crucial transportation corridors cross volcanic drainage channels that are now filled with hardened Lahar deposits up to 4 meters deep. Full reconstruction of the infrastructure will require comprehensive geological surveys to determine which routes remain critically vulnerable to future flows, potentially leading to the necessity of redrawing the entire transportation map of whole provinces. The economic implications of this disaster compound daily, pushing communities further into crisis. Agricultural damage has already reached 142.29 million Philippine pesos, a devastating blow to the nation's food supply. Thousands of hectares of vital rice and cornfields are now buried under volcanic debris that will require complete and costly soil replacement before any farming activities can resume. Power restoration efforts face similar, unique geological obstacles, as transmission towers in affected areas now sit precariously atop unstable Lahar deposits rather than anchored on solid ground. The meteorological forecast for the coming weeks and months compounds these concerns exponentially. The Philippines remains squarely in its peak typhoon season, which typically runs through December. Pacific water temperatures are still critically elevated above thermal energy source that continues to fuel additional intense storms. Each subsequent rainfall event, specifically any event above the threshold of 50 millimeters in affected areas, carries the immediate potential to remobilize the fresh Lahar deposits. This creates a terrifying, persistent cycle of recurring geological hazards that could easily persist not just for months, but potentially for years to come. Because what happens next has the power to rewrite the evacuation maps across 3 major island groups. The volcanic threat timeline remains completely unpredictable and is potentially multi-year. PHIVOLCS continues its intensive 24-hour monitoring of all affected volcanic areas, utilizing seismic stations, thermal sensors, and real-time precipitation gauges. However, the data reveals a profoundly uncomfortable truth to the scientific community. Lahar prediction remains more an art than a definitive science. Unlike volcanic eruptions, which almost always produce measurable seismic precursors hours or days in advance, rainfall-triggered debris flows can begin with minimal warning across multiple drainage basins simultaneously. The current volcanic alert levels have not officially changed. Mayon remains at alert level 3, and Canlaon is at alert level 2, because the volcanoes themselves are not exhibiting increased eruptive activity. Magma chambers remain stable. Gas emissions show no significant changes, and ground deformation measurements detect no unusual swelling or subsidence. The true danger, therefore, comes from above, not from below. Every weather system that now approaches the Philippines represents a potent geological trigger for millions of tons of loose, saturated volcanic material that is sitting ready on the slopes. International volcanic monitoring specialists describe the current situation as unprecedented in both scale and complexity. The Volcano Disaster Assistance Program has meticulously documented individual Lahar events at dozens of volcanoes worldwide, and single volcano scenarios, such as the Pinatubo crisis, have been extensively studied and documented. But never before have multiple volcanic systems responded simultaneously to sequential super typhoon impacts across such a condensed time frame and confined geographical area. The implications of this new reality extend far beyond the scope of immediate emergency response. Agricultural areas in the affected provinces may remain unsuitable for farming for multiple growing seasons. This is because Lahar deposits fundamentally alter soil chemistry, change vital drainage patterns, and radically reshape the topography in ways that conventional agricultural recovery methods simply cannot address. Some severely affected areas may require complete soil replacement, a complex, expensive, and protracted process that could take years and cost billions of pesos to execute. Furthermore, reconstruction planning must now factor in entirely new geological hazard zones that did not exist even 2 weeks ago. Settlements that have existed safely for generations now suddenly find themselves situated directly within newly active volcanic drainage channels. Urban planning officials across the region face the unprecedented and monumental challenge of potentially relocating entire settlements while simultaneously designing critical new infrastructure around volcanic hazards that may persist indefinitely. They must plan for a multi-year, multi-system threat. Perhaps most unsettling of all, the twin typhoon scenario that triggered these catastrophic flows remains climatologically possible throughout the remainder of the 2025 tropical cyclone season and beyond. Pacific water temperatures exceeding in atmospheric patterns that enabled the rapid intensification of both Calmegi and Wong show virtually no signs of stabilization. In fact, most long-term climate models suggest that similar compound storm events may become increasingly and tragically common in this region. The Philippines has weathered countless typhoons and numerous volcanic events throughout its recorded history, successfully developing resilient communities and sophisticated disaster response protocols. However, the convergence of extreme meteorological events with multiple volatile volcanic systems creates an entirely new category of compound natural hazard. This is a threat of unprecedented scale and complexity, one that may be physically and logistically impossible to fully prepare for until it happens again. The world is watching to see how this nation handles the complex, terrifying aftermath of its double storm disaster.